Hello everyone, I'm Qiu Zhikai. I'll be starting our presentation with the data profiling and the quality diagnosis phase. For this project, we are using a classical financial dataset focused on predicting credit defaults over a 2-year period. To give you a high-level data overview, our dataset contains 150,000 observations across 11 features. As shown in our initial scan, all variables are numeric, consisting of 7 integers and 4 floats. While this uniform data type might seem very straightforward, our systematic exploration reveals that beneath the surface, the data requires significant cleaning and validation to be suitable for reliable AI modeling. Moving into our systematic profiling, the non-new accounts immediately highlighted the major data integrity issues. Specifically, monthly income is missing nearly 20% of its entires, and number of dependents is missing about 2.6%. In the context of the credit risk, income is a fundamental pillar of the repayment ability, so these gaps represent a significant hurdle for the data governance. Furthermore, we identified a coding fallacy within the delinquency features. Certain records use 96 or 98 as the placeholders. If left untreated, a basic machine learning model would interpret this as nearly 100 late payments, which would severely distort the model's behavior. Next, we addressed the analytical fallacies through the visualization. Our box plot detected the extreme outliers in revolving utilization and debt ratio. Figures so high they are effectively physiologic impossibilities in a standard banking environment. Perhaps most striking was finding a borrower with an age of 0, a clean data integrity error. Identifying these outliers at this stage is crucial. It allows us to justify our data-centric decisions and prevent the model from declining from noise or anomalous entries. Finally, we analyzed our target variable, serious delinquency in 2 years. We found a significant class imbalance, with only 6.7% of the population defaulting. This confirms that occurrency is a poor metric for success here. This EDA phrases has provided the evidentiary basis for our subsequent workflows, where we will compare the minimally processed data against the fully processed data to demonstrate how rigorous prepared impacts the performance. Thank you, and I will handle it to my teammates.
Hi, I'm Xie Xiaofan. I will be walking you through the data pre-processing part of our project. First, let's look at the age feature. In the original dataset, we find a lot of zeros. Since people can be 0 years old, these are clearly errors. To fix this, we calculate the median age ignoring those zeros and use it to fill in the gaps. If you look at the comparison plot, the green area shows the processed data. You can see the spike at 0 is gone, and the distribution looks much more realistic now. Next up is the number of dependents. We had some missing values here too, because this is a discrete feature, meaning whole numbers. We use this simple imputer to fill them with the median. By looking at these two count plots side by side, you will notice the trends are almost identical. This means we complete the dataset without changing its overall character or adding any bias. Finally, we have monthly income. This was a critical step. We know that income usually depends on age, so we didn't want to just use one simple median for everyone. Instead, we split the ages into 4 groups and filled the missing income values based on the median of each specific group. Check out the chart on the right. Even though we have more data points now, the green after curve still follows that original skewed shape perfectly. This keeps our data honest and ready for model training. Thank you.
Okay, now this is my part. Building on the initial data profiling and basic cleaning discussed by my teammate, I will now dive into the advanced pre-processing stages, where I focus on ensuring data robustness, addressing ethical bias, and extracting deeper financial insights. In this first stage, I prioritized outlier governance. My exploration revealed that variables like debt ratio contain extreme physically impossible values, some exceeding 300,000, which will severely distort model weights. To handle this, I applied winsorization, capping these features at the 99th percentile. This allows me to retain the high-risk signal of these outliers without introducing mathematical noise. Simultaneously, I parsed records containing codes like 96 and 98 from the columns, ensuring that our training data is grounded purely in verified credit history. Next, I addressed numerical stability and fairness. As shown in the histograms, monthly income was heavily right-skewed, so I applied a log transformation to normalize the distribution, which is essential for convergence. More importantly, I conducted a bias analysis regarding age. I discovered a significant disparity. Applicants under have a rate nearly 4 times higher than those over 60. This is a critical governance finding, as it warns me that a model trained on raw data might discriminate against younger borrowers. This finding directly informed my strategy for the next stage, feature engineering. To address the skewness and bias I just identified, I developed a suite of engineered features. Instead of relying on raw, potentially biased demographic variables, I shifted the focus to behavioral and economic indicators. For instance, I derived income per dependent to better reflect a household dual solvency. I also consolidated fragmented records into a whole time past due signal to capture chronic debt credit behavior. By creating the high-risk lag, I've explicitly highlighted individuals in severe distress. I designed this feature specifically to mitigate the age bias identified earlier. By emphasizing what a borrower does rather than who they are, I'm able to maintain high predictive accuracy while ensuring the model remains ethically sound and governance compliant. Now that I have finalized a dataset that is structurally balanced, feature-enriched, and ethically audited. It is ready for the modeling phase. I will now hand over to Zhu Yuting, who will demonstrate how this data decisions translate into actual model performance. Thank you.
Hi, I'm Zhu Yiting, and now I will be talking about design of AI algorithm. For the design of AI algorithm, we focus on logistic regression and decision trees. Linear regression was not suitable because the target variable is categorical. The target variable determines whether a borrower experienced serious delinquency in the past 2 years, with 1 meaning yes and 0 meaning no. Logistic regression was chosen for its effectiveness in predicting binary outcomes, and its ability to show how each feature impacts the prediction. On the other hand, decision tree can uncover nonlinear patterns in the data that logistic regression might overlook. Next, we compare model performance on minimally preprocessed data versus fully preprocessed data. For the minimally preprocessed data, missing values were handled by median imputation, and class imbalance was addressed by setting class weights to balance. This gave us an accuracy of 0.77, ROC AUC of 0.8, and a recall of 66% for the high-risk group. For full preprocessing, we handle outliers by doing sample removal and also capping extreme values, and applied smooth to balance the classes. The accuracy stayed similar at 0.78, but ROC AUC improved to 0.85, showing that our model is now better at detecting high-risk borrowers. Precision is also improved slightly to 20%, indicating fewer false positives. Now, let's look at the most important features in our logistic regression model. The top 3 features predicting serious delinquency are total time past due, revolving utilization of unsecured lines, and age. Borrowers who have more overdue payments in the past are much more likely to become serious delinquent. High credit utilization also increases delinquency risk. On the other hand, age has a negative effect. Older borrowers are generally less likely to experience serious delinquency, which could reflect more financial stability or experience in managing credit. Finally, let's look at decision tree model. Decision tree model achieved an accuracy of 0.79 and RLC-AUC of 0.84, which are similar to the result of the logistic regression. As a non-parametric model, the decision tree doesn't rely on strict assumptions about the data, which is a key advantage. However, it can be sensitive to small changes, so even minor variation in the data can lead to different trees. As our dataset is quite large, the trees become quite complex and harder to interpret. In summary, both models offer valuable insights. Logistic regression allows us to measure how each feature influences the outcome, while decision trees are effective at identifying complex, nonlinear relationships in the data. Now I will pass the time to Xie Xiaofan to do the conclusion.
Our model successfully identifies high-risk borrowers by focusing two primary drivers: past due behavior and credit utilization. The most significant takeaway is the impact of smooth balancing. Initially, our model was missing the vast majority of defaults, with a record of only 15%. By balancing the dataset, we boost that record to 74%, increasing our ability to catch potential defaults before they happen. Overall, this provides a robust, interpretable framework that allows the bank to move from reactive to proactive risk management. Thank you.